Hello everyone, this is Dr. K. Ramya, Assistant Professor, Department of Humanities and Sciences, Nanomaterials Institute of Technology and Sciences, Tirupati. In the present session, we are going to discuss about the characterization techniques. So what are the characterization techniques? Characterization techniques exactly gives the characteristics of the material we have prepared. That may be a thin film material or a nanomaterial or a bulk sample. We are going to detect what is the analysis. So how far we have achieved our material, whether it is the material we have expected or not. So the two characterization techniques we are going to discuss in this session is, one is what we call it as XRD, X-ray diffraction, that gives a structural analysis, structural arrangement, how the material has been formed. Is it the design structure we have needed, or any other phases are present in the material apart from the phase what we are opted for, and hence whether the structure is changed or not. So all these details are given by X-ray diffraction. So second one is what we call it as SEM, that is scanning electron microscope. So by using scanning electron microscope, we are going to see how is the morphology of our material. So how the atoms are allocated in our material. So what is the distance between the atoms present in our material. Whether all the atoms have the same interatomic distance or various of the interatomic distances, or there is huge difference between the atoms, huge distance between the atoms. And what is the grain size of the atom present in our sample. All the details are given by scanning electron microscope. So let's get started. So XRD, X-ray diffraction. I have told you that we are going to analyze the structural analysis, structural studies. So, but before going deep into how we are going to analyze the structure, so here first we have to know why we are using X-rays instead of all the other rays. So why we are using X-rays? X-rays have electromagnetic radiation with high energy photons with 100 electron volts to 100 kilo electron volts. But we will use for X-ray diffraction, for all the diffraction purposes, we use only the short wavelength X-rays, because the wavelength of the X-rays is comparable to the size of the atom. So why we are using XRD is that the wavelength of the X-rays is comparable to the size of our atoms, which will be ideal for determining the structural analysis. Even for the bulk structure, what happens is that the X-rays will go deeply into the sample and penetrate into the sample and gives the details present in the materials. And hence, this is the reason, these are the reasons why we are using X-rays in our analysis, that is structural analysis. So how we are going to produce the X-rays? So production of the X-rays is by X-ray tubes or synchrotron radiation, but many primary sources, many places we use only X-ray tubes to produce the X-rays. So what is the principle underlying in the production of the X-rays? When the fast moving electrons go and hit the target, hard target, then what are produced is X-rays are produced. So electrons will collide with the atoms in the target and are slowed down. Then a continuous spectrum of X-rays is produced. So it was first discovered by the scientist called as Rontgen. Actually, he don't know how to name the rays that are coming out, and hence he called it as X-rays. As we say in the math, let the value be X. So that's how the X-rays has come. So X-ray name has come. So what are the commonly used targets here? That is copper, molybdenum. So the fast moving electrons can either hit copper or molybdenum. How much it will emit? It emit 8 kilo electron volt and 14 kilo electron volt energy. What is the wavelength range? Wavelength range will be in the form of 1.54 to 0.8 angstroms respectively. That's how we produce the X-rays. Right. When X-rays collide with the electron, what we have saying is when the fast moving electrons goes and hits the target, then X-rays are produced. Right. Suppose that when X-rays collide with the electrons, what happens during that collision? Some photons from the incident beam are deflected away. Those are flied away. So apart from the region where they are originally traveled. So when the X-rays collide with the electrons, then two types of scattering are possible. One is what we call it as elastic scattering. Another one is what we call it as inelastic or Compton scattering. So elastic scattering or Thomson scattering, inelastic or Compton scattering. So what is the basic difference is, it again depends upon the wavelength. So if the wavelength of the scattered X-ray, so X-rays are coming and colliding with the electrons and getting scattered. So if the wavelength of the X-rays before the scattering and after the scattering is not changed and only the momentum is changed, then we call it as elastic or Thomson scattering. Suppose that if the wavelength of the scattered X-rays changes after the scattering, then it is called as inelastic or Compton scattering. So depending upon the wavelength of the X-rays before the scattering and after the scattering, scattering is divided into elastic and inelastic scattering. Right. And so this is very important. So we'll discuss while we are studying with the analysis. Before going that, so see here, this is the incident X-ray. For instance, this is your sample. So incident X-rays comes and hits the targets, scattered. So incident X-rays and the scattered beam to detector. Similarly, this is called as transmission. This is reflection. See, just it is going, hitting, maximum it is scattered. So here what's happening? Incident X-rays are coming, hitting the target, and then what is happening? Scattered beam is there, but this is a transmitter beam. See, there is a difference here. So this is reflection and this is what we call as sample transmission. So this is the detector which detects the X-rays, right? We'll get back to here later. So before that, we are going to see about the Bragg's law, a very much important, and without this Bragg's law, there is no XRD or there is no structural analysis. So what is the Bragg's law? First of all, atoms are arranged in the periodic fashion. See how the atoms are arranged? These are how the atoms will be arranged in the crystal. So in a periodic fashion, there will be some same interatomic distance. So this one is called as one lattice plane. This one is called as second lattice plane, third lattice plane, and so on. The distance between the two lattice plane is given by D. So D is called as interplanar distance. So this is plane 1, plane 2, plane 3, and so on. So distance between any two planes is what we call it as D. So that is interplanar distance that is given by D. So right. So this is what we call as lattice plane. Right. So what happens, how the X-rays are generated, let us see. And so this is the interatomic distance. The distance between two atoms is what we call it as interatomic distance. Right. These are the X-rays. So the incident beam is coming and incidenting on one particular atom. It is getting reflected. Let us just now see only about reflection, not about the transmission. So again, what is happening? Another electron, another incident ray is coming, hitting on the target. That is the atom, again reflecting. So what is happening here? There is some angle between the two planes. This is theta, this is theta. So on the whole it is sine 2 theta. So 2D n lambda is equals to 2D sine theta. Sorry, this is the angle of incidence. 2D is the interplanar distance. So 2D sine theta is equals to lambda. N is the order of the diffraction, and hence if n is equals to 1, then lambda is equals to 2D sine theta. This is what we call it as the Bragg law. So X-ray beam is interacting with the atom. So by Bragg's law, n lambda equals to 2D sine theta. Lambda is the wavelength of X-rays we have used. N is the integer, that is the order of the diffraction, and theta is what we call it as scattering angle. Right. So this is all about the Bragg's law. Fine. So what happens? These diffracted rays from different atoms interfere each other, and that's how the diffraction occurs. The resultant intensity is modulated by interaction. So how these are, and the peaks in the XRD are directly related to atomic distance. So we have seen here like, so one peak, one scattered angle, another scattered light, another. So what happens is at one point these scattered lines on the scattered radiations will interfere, and hence it gives to which pattern? Diffraction pattern. So that is called as the XRD, X-ray diffraction. So this is one scattered beam, another scattered beam come, another scattered beam come. So all of this what happens is interfere at one particular point. So after interference what happens? Let us see. Right, this is what we call as X-ray powder diffraction. So this is most widely used in X-ray diffraction technique. The sample form may be normally in powder. Sometimes it may be also the liquid. So let us see how it will be there. So this is the XRD pattern. So x-axis will be 2 theta, right? Y-axis will be intensity, right? So x-axis will be the 2 theta values, y-axis intensity. You can see very sharp lines here, sharp peaks here. These sharp peaks, this sharp peaks indicates that your material is a crystalline material. Suppose there is no sharp peaks and you have much of noise here as you have here, means your material is amorphous. Right, why XRD is used? Already I have told phase identification. So for example, if you are preparing a material like copper sulfide, CuS is your material. But while preparation of the material, your copper content is more, right? Then CuS, CuS2, Cu2S3, different phases are formed. So how do you rectify? How do you form? So these are the different peaks we have. So how to identify the peak? So there is a software called as database JCPDS, Joint Committee on Powder Diffraction Standards. So by using that, we can see whether this material has only one phase, two phase or three phases. So binary phase, ternary phase or single phase. So if you are preparing a material, so you can identify the phase depending upon the structure of the material, and you also know the structure. So JCPDS gives the structure of the material and the phase identification. For example, diamond and graphite. So both are made up of carbon atom. But still, these diffraction lines, what it states is that whether it is a diamond or whether it is a graphite, that can be obtained by using the JCPDS. So already we have discussed that data can be collected by using transmission geometry or reflection geometry. So what is the basis for XRD? Bragg's law is the basis for XRD. So what are the applications we have discussed? So identification of the unknown crystalline material. What is your material? So depending upon these peaks, we can see what is the material. Determination of unknown solid, unit cell dimensions, A, B, C, or the unit cell dimensions, lattice parameters. You can find out the lattice parameters by means of the XRD. Measurement of sample purity. As I have said, you want only CuS, but your material has Cu2S. So your material had lost its purity, right? The determination of the crystal structure. So what crystal structure? There are 7 crystal systems: trigonal, tetragonal, monoclinic, rhombohedral, hexagonal, triclinic, everything, cubic. So these 7 crystal system, out of these 7 crystal system, which crystal system is your material? Crystal structure is your material. That can be identified by using XRD. Right. Next, we move on to very, very important technique and very sophisticated technique called as scanning electron microscope. In the scanning electron microscope, total SEM. SEM means scanning electron microscope. It consists of 2 parts. One is what we call it as electronic console. Another one is what we call it as electron column. So see here, this is a schematic of the scanning electron microscope. So all the outer layer, that is the magnification control, scan generator, display, and amp. So amplifier, amp means amplifier. All this brightness, contrast, these all comes under electronic console. So this part comes under electronic console. This and all is what we call as electronic column. So this is called as electronic column. This is called as electronic console. So total everything made together gives our SEM. So this is another schematic. Here you can see. So electron gun, all this magnification, everything same. But where the secondary SE means secondary electrons. And what is BSC? BSC is what we call it as backscattered electron. So let's see the phenomenon. So this is the electron gun. So here we are using, so in X-ray diffraction, we have been using the X-rays, right? Here SEM, we are using the electrons. So electron beam is focused onto your sample. So here is your sample specimen. This is your specimen. From the electron gun, we are targeting the specimen by means of, we are focusing the specimen by means of the electron beam. So first what we have to do is that first part, this is the electron column. So the first part is what we call as electron gun. So electron gun by thermionic emission. So we have a tungsten filament here. Filaments control this filament control the number of electrons coming out, right? So by using the thermionic emission by means of a tungsten filament, free electrons are generated from the electron gun. So once the free electrons are generated in the electron gun, they pass the condenser lens. Here the first condenser and second condenser will be somewhere in the second column, right? And so here I have shown both the condenser at one place, right? So it passes through the first condenser lens. So why we are using the condenser lens is to converge the electrons. Electrons will be coming endlessly, boundlessly from here. So to narrow as thin as possible, we are using the condenser lens. So how much thin length of electron, thin beam of electrons you have, that determines the intensity of your that goes and falls on your specimen. There you have interaction. Suppose number of electrons are coming and they are targeting the specimen, then we cannot have the exact replica of the data. Next one, we have apertures here. So this is a final lens aperture. Before that, we have two apertures, spray aperture and another one aperture here. These apertures depends upon the microscope. Some microscope have many number of apertures. Here we have two apertures. These apertures are used to exclude or to reduce the extraneous electrons, so extra electrons and all. So we are filtering the number of electrons. See, the thinness of the electron beam is getting filtered out, right? So this final lens, it determines the diameter of the spot size of the beam. So decrease in the spot size gives increase in the resolution. Decrease in the electron beam gives increase in the resolution and depth of the field without any loss of the brightness. So we have electron gun, condenser and spray apertures, final lens aperture, and the electron beam is coming and falling on the sample. So this is about the electron column. Then what happens after falling on the sample? It is going to the scanning system, this part, right? So images will be formed. So this will be detected by the detector and the signal will be amplified and displayed via the scan generator. So what happens is images will be formed. I will show you how the images are formed. So rastering the electron beam across the specimen by means of the objective lens. So stigmatter, so a very important thing, here it is not actually included. Stigmatter or a stigmatter connector is used for correcting any aberration. So for decreasing any noise present, it is used. And finally, the specimen chamber, that's also not here. It is a lower portion of the column, right? So where the controls are located. So here you can see there is secondary electrons and as well as the backscattered electrons. So this is a schematic: electron gun, condenser lens, what do you call it as apertures, scan coil, specimen and detection unit, right? So these are the things we have discussed. Then with the optical microscope, specimen resolutions will be 0.2 microns or else it will be 25 angstroms. So there will be two types of signals coming from the cell material. What are they means? Secondary electrons and backscattered electrons. So I have shown in this diagram. So secondary electrons will be detected at some place. Backscattered electrons will be detected at some other place. Now we'll see how we analyze. So we are just sending the electrons, beam of electrons converged and thin beam of electrons onto the specimen. After it hits the specimen, what's happening? There are two types of scatterings. One is secondary electrons will come out and backscattered electrons will come out, and finally we are going to see the image. So what are the secondary electrons? So secondary electrons are due to the result of the inelastic collision and the scattering of the incident electrons, right? The incident electrons will come and fall on the sample, and the secondary electrons are produced due to the inelastic collisions of the incident electrons with the specimen electrons. So these are the secondary electrons. So what are the backscattered electrons? Elastic collision and the scattering between the electrons and the specimen. So only thing you have to keep in mind is that how is the specimen, how are the electrons. If it is due to the inelastic collisions, secondary electrons will happen. If it is elastic collision, backscattered electron will happen. We have discussed what is inelastic and what is elastic. So two types of signals in the SEM are secondary electrons, backscattered electrons. Secondary electrons are due to the results of the inelastic collisions. Backscattered electrons are due to the result of the elastic collisions. Between what and what? Between the electrons as well as specimen. So both of them give some detail. So the first one gives the surface structure of the material below or on the range of 10 micrometer. So backscattered electrons greater than 1 micron. So both of them give information but in different various energy ranges. So this is what we have discussed. So see, in elastic collision, secondary electron, backscattered electron, electron collision, elastic collision. So right, so this is the SEM image. So this is the FE-SEM image. Here I want to tell you that there is a slight difference between SEM and FE-SEM. So SEM is what we call the scanning electron microscope. FE-SEM is field effective scanning electron microscope. So what is the difference is that in the field effective, we have the emission gun, right? So we have seen an emission gun here. So this electron gun. So this emission gun in the case of field effective will focus more. So it focuses more. It can even focus the lowest energy electron beams. Even the electron beam range is very less. This field emission gun will focus us, and also the lens detector will have very high resolution in the case of FE-SEM. So that's why it's very clearly here. This is taken from my thesis. And so this material is cadmium sulfide. See, it has a polyflower morphology. If the atoms are like this, it is called as polyflower morphology. See, here it is very densely coated at some areas, right? So this is the grain, and we have to find the grain size. The grain size is around some 60 nanometers to 80 nanometers for this sample. So these are the SEM images of one of my students, right? See, the interatomic distance, the atoms are very far apart. So at one condition, we got the atoms or the grains are very far apart. Here it is densely placed. So this is what we call it as needle-shaped morphology. See, it is in the form of needles. So it is a needle-shaped morphology. Here number of grains, here one big grain is there. This is what we call it as agglomeration of grains. So see, number of grains are accumulated at one particular place, agglomeration of grains. So these are the FE-SEM images. See, these are SEM images. See, it doesn't have that much resolution. So only you can see on the top view. So whereas you can see here how the distribution of the atoms are there, what is the morphology and all. So this is also valid, but still you cannot have that much details in the SEM. So what are the applications? So we can know semiconductor investigation completely lays on our SEM. So for the high temperature superconductors, SEM is used. Even for forensic investigations, it used. And one more important thing is that by using the energy dispersive analysis of X-rays, I have written here, so we can know the composition of the material. So previously we have discussed, right, for CUS, if you want to prepare CUS, by using XRD, we can know the phase, what are the different phases, whether it is CUS or CU2S or CU2S3 or so on and so. So that is the phase identification we have been using there. But what is the composition? You have prepared CUS. So is the XRD only you have to relay, or by using the energy dispersive analysis of X-rays, EDAX? Okay. So by using that, we can find out the chemical composition, how much copper is present in your material, how much sulfur is present in your material. So apart from copper and sulfur, whether some other contaminants are there and so on. So that is attached normally with some FE-SEM with EDAX or SEM with EDAX. But I'm not going to discuss that because that is out of the phase of the syllabus. So these are the two characterization we have discussed. XRD is used for structural analysis to know the structure, and SEM is used for the morphological analysis, how the atoms are allocated in your material, and what is the grain size of the material, what is the interatomic distance, and so on. So, right? So these are the quick references. Thank you.